All right, welcome everybody. Welcome. Thank you for joining us. Um, really appreciate you spending a little bit of your New Year's day with us. Happy New Year's, everybody. I hope you had a nice Christmas break so far. Had a nice New Year's Eve last night. Um, for those of you who have never joined us before, my name is Brian Jackson. I'm a professor in the physics department at Boise State University, where I teach physics and astronomy. And you are tuned in to the First Friday Astronomy events. This is a monthly lecture series where we have someone come in on the first Friday of every month, 7:30 p.m. Mountain Time, most of the year. And we invite some kind of a space scientist. In some cases, we invite folks who work in space policy. We've got some space science educators lined up for the series of lectures this semester. And so I hope you enjoy it. As I said, this happens every month on the first Friday, 7:30 p.m. Mountain Standard Time or Mountain Time, whatever whatever we're in at the time. Let me just give you a little heads up, a little taste for what's coming up this semester. Um, so today, of course, is January 1st, and I'm going to talk a little bit about a project that I've been working on. Gosh, it's probably been almost 3 years now, about the history of the discovery of Neptune. In February, we're going to host Lisa Grossman. She's a journalist for Science News magazine, and she's going to tell us a little bit about how scientists talk with journalists and sort of good strategies for public communication. I think that'll be really fascinating. She's done a lot of really great science reporting over the years. Um, in March, we are very, very, very fortunate to get Professor Lindy Elkins Tanton of the School of Earth and Space Exploration in Arizona State University. Guys, you need to look her up. She is a powerhouse in space science. And we were very fortunate to get her. She told me the fact that our event is scheduled on Friday evenings meant we could just squeeze into her calendar. If we had invited her at a normal time, we probably couldn't have gotten her. She is the principal investigator for NASA's Psyche mission, which is a journey to a metallic world. I think that'll be a really fascinating talk. So if you can tune in for that, I highly, highly recommend it. And then we're going to have Dr. Amy Cho from the Dr. Amy Choi from the Department of Physics at Ohio State University, and she's going to tell us a little bit about gravitational lensing and how that technique is used to study the universe. Unfortunately, these talks are all going to be virtual. With the COVID situation, it's hard to do them in person. We will hopefully be able to do them in person again. But one advantage of that is that they are live streamed and then automatically recorded on YouTube. And so if you have a friend or a relative or somebody who wants to attend one of these talks and just can't make it on a Friday at 7:30, they're welcome to just tune in. They're just posted for free on YouTube. I've linked to them from my website, so you can find them there. This series of lectures is entirely supported by the public. So folks like you are donating to support this. This is the kind of stuff you like to see on YouTube, you like to see on the internet, please visit our website there at the bottom, give.boisestate.edu/astronomy, and that'll send you right to the link for the university's foundation where you can donate to this account, to these events. These still cost money, even though they're all virtual. We're still paying for things. So please, if you can, feel free to donate. We have another treat coming up for you this semester. Well, actually, let me get to that. I'll get to that in my talk. Excuse me. Let's see. We will have some really great things coming up later that I'm going to talk about in a second. So today I'm going to talk a little bit about my research into the history of the discovery of Neptune. I will admit to you that I got to working on this lecture earlier this week, and it's such a fascinating topic. It's so rich that I just barely finished this lecture before before the event tonight. So bear with me. I'm just so passionate about this topic. It's so fascinating. If you have questions that you would like to ask, you are welcome to ask them over the YouTube chat. I see it. You can see it here. Here's the chat window. Nathan McGregor, who's very kindly, one of the students in the physics department, has very kindly offered to monitor the chat there and to collect your questions and send them over to me. So as you have questions, please feel free to type them into the chat window, and Nathan will is he's on top of it. He'll get to your question and relate it to me. So by the end, we should be able to get your questions. Okay, so this is the first Friday event. We're going to start a new series of events this spring that we're going to call the Third Thursday Planetarium shows. So many of you may know that we raised funds to purchase a mobile inflatable planetarium recently. Unfortunately, we can't purchase it. We can't use it because of the COVID situation. And so in lieu of giving in-person virtual planetarium shows, we're going to start a series of virtual planetarium shows. So on the third Thursday of every month, so we got first Friday, that's lecture. Third Thursday at 7:30, we're going to do a virtual planetarium show. So we'll live stream a virtual planetarium show like this. The first one of these is going to be on January 21st. So that's the third Thursday of January. They're going to be informal Zoom sessions. So we'll invite you into a Zoom session. For those of you who haven't done Zoom yet, this is your chance. You'll be able to join a virtual Zoom session. And what we're going to do is we're going to talk about how to do basic stargazing. We'll discuss observing challenges, maybe answering questions about how to use a telescope. They're going to be kind of informal. Maybe you want to think about them less like lectures and more like kind of like astronomy troubleshooting. If you want to do stargazing, we want to help you figure out how to do that. That is still a perfectly safe thing to do nowadays as long as you're socially distanced. But because those events are going to be in a Zoom session, to avoid Zoom bombings, we ask people to sign up for them. So if you're interested in joining us for a third Thursday coming up, please go to this link down here. It's boi.st, so like Boise State, BOIST/third Thursday. Okay, if you go to that site, it'll send you to a Google form where you can just fill in just your name and your email address. That's all we're asking. And then you'll get an email the week before the event with a link to the Zoom session so you can join us there. And again, it's super informal, totally free and open to the public. We just ask that you register first so we can keep track of who joins us in the Zoom session. All right. Let's talk about Neptune. Neptune is, so far as we know right now, the most distant planet from the sun in our solar system. And because it's so distant, there's actually a lot about Neptune we still don't really know. The most nearby observations that were ever collected were collected by during the Voyager's flybys in the late 80s. And that's the closest we've ever been to Neptune and the last time we were close by. So I'm going to show you just a real quick video from National Geographic, which is a really great summary of our knowledge of Neptune.
Edges of the solar system, it floats. Anchored by a star, but barely graced by its warmth, this traveler drifts alone, as deceptively calm and elusive as the deep blue sea. Neptune is the 8th planet from the Sun. At about 30 times the distance between our star and the Earth, or 30 astronomical units, Neptune is the most distant planet in our solar system. This distance creates the longest orbit of the 8 worlds, about 165 years, with the seasons lasting a little over 40 Earth years each. Being so far away from the heat and light of the Sun, Neptune is cold, dark, and icy. At its heart is a solid core about 1.5 times the size of Earth. Making up about 45% of the planet's mass, the core is made of water ice and silicate rock. The rest of the planet is believed to be a hot, pressurized ocean of water, methane, and ammonia ices surrounded by a layer of clouds. These clouds, predominantly made of hydrogen and helium, include traces of methane, which give this ocean world its rich blue color. While the clouds create a cool, calm veneer from afar, up close they are whipped around by the most severe weather in the solar system. Winds on the planet reach speeds of over 1,200 miles per hour, nearly 5 times faster than the strongest winds recorded on Earth. In fact, the winds are so powerful that they break the sound barrier.
And so that's just a little taste of what we know about Neptune nowadays. As I said, we had the Voyager missions that flew by in the late 80s. There are missions on the books right now that are in planning from NASA to visit the Neptune system again. One mission is called Trident. And Trident is a mission that's not actually focused on Neptune. It's focused on Neptune's largest moon, Triton. Um, Here's a little schematic showing Triton. Triton is a fascinating object. Triton almost definitely didn't form with Neptune. It was probably captured from the outermost regions of the solar system. Um, Triton is volcanically active at some level. We see actually there are plumes, volcanic plumes erupting, or maybe geysers. We don't know exactly what they are, that were observed by the Voyager spacecraft. There's evidence of the surface for active geological processes, and so this is a fascinating world. It will be a long time before we return. Of course, the mission is still in planning; it's not even been launched, so it will be decades before we return. But Neptune wasn't always like this. Neptune wasn't always this rich world, this rich system with a moon. A long time ago, maybe not too long ago, actually, Neptune was simply a point in the sky. And even before that, actually, Neptune was unknown. Neptune is one of the two planets that were discovered in the modern era. And so I want you to send your mind back in time, back to September 23rd, 1846, a very specific date and very important in the history of astronomy. Imagine that you're at the Berlin Observatory there in September 1846, and you're standing in the observatory with a recent PhD student. This is someone who just got his PhD and a student intern. These two men are very excited. They're looking through the telescope there at the Berlin Observatory, and they slew the 9-inch Fraunhofer refracting telescope. This is the pride of the Berlin Observatory, to a very specific coordinate. They seem very intent on getting to this very particular place in the sky. Right ascension 22 hours, declination minus 13 degrees. This is the very spot predicted to host an as yet unknown planet, a new mysterious member of the solar system. With that very region in sight on the telescope, the PhD graduate student struggles to see an object with an extended disk. So those of you who've done stargazing before know that no matter how high a magnification you use in your telescope, stars always appear as point sources. But planets will be extended disks. They'll actually show you some size if you put in a large enough magnification. And so this PhD student, this PhD graduate, is struggling to see the extended disk of an object in the field there. This is the telltale of a planet. Instead, he can only recognize a very narrow field of stars, one star after the other. None of them is obviously disk shaped. And so he turns to the intern and asks for the student to retrieve a map, a newly published map of this region of the sky, which contained a fuller inventory of this region than any chart that had been previously available. With the intern scouring this map, the PhD called out the positions and magnitudes, the brightnesses of each of the stars that he saw in the sky in the telescope, checking to see if anything was out of place. Anything out of place could be the new planet that they were excited to find. After listing only a few, the PhD graduate described a star of 8th magnitude at a right ascension of 22 hours, 53 minutes, 25 seconds. And before he could even get out the declination, the other coordinate for this object, the intern interrupted to say, "That star is not on the map." That was Neptune, discovered on September 23rd, 1846 at the Berlin Observatory by Johann Galle and Heinrich d'Arrest. Galle was a recently graduated PhD student, and d'Arrest was essentially an intern there at the observatory who had begged to help Galle conduct this search. This was the very first night of the search, the first time they had gone looking for this predicted planet. This discovery was unprecedented in human history because it was the first planet that was seen in a person's imagination before it was actually seen in the sky. It provided powerful confirmation of Newton's theory of gravity, which up until that point had been somewhat in question for reasons that we'll get to later. But more than that, its discovery excited waves of international controversy, and it kept one country from reclaiming the mantle of ascendancy in science that it had once had, while enlarging an already impressive edifice of scientific achievement for another country. To understand this story completely, though, we need to go back to before 1840s Berlin. We need to go back almost 2,000 years to really understand why this discovery was so important. So this is a really beautiful illustration showing what ancient astronomers thought was the whole universe. This is Ptolemy's geocentric model for the solar system. So Ptolemy was an ancient astronomer in about 140 AD, and he wasn't the first person to put this picture of the universe together, but he was the first to systematize it and publish it. Ptolemy and the ancient astronomers imagined that the entire universe was centered on the Earth, that the Earth was the center of the universe, and all the stars and planets revolved around the universe, the sun, the moon, the stars. And that's not a crazy idea. If you think about it, if you look at the night sky, you look at the sun, you look at the moon, they're clearly in motion in the sky, and you don't feel like you're moving at all. So it was very natural to assume that the Earth was the center of the universe and that everything else revolved around the Earth. And so Ptolemy and other ancient astronomers believed that all of the planets, and now planets here includes not just those objects that we now call planets like Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Planets also included the moon and the sun. They were basically objects that were not fixed in the sky that wandered around. And so you can see here in the model for the universe, those the orbits of those objects highlighted in the map. So here's the moon, there's Mercury, there's Venus's orbit, the sun, Mars, Jupiter, Saturn. And then the firmament, that's the firmament of stars, very, very distant, far, far away. And so for ancient astronomers, this was the entire universe. There was nothing known beyond the solar system. And it was believed that the entire solar system was orbit around the Earth. This model had built into it this assumption that the orbits of all these objects were circular. So basically were these perfect circles orbiting the sun, or orbiting the Earth, excuse me. But as observational astronomy progressed over hundreds and even thousands of years, there became these important discrepancies between what this geocentric model premised on circular orbits predicted for these motions and what was actually observed. And one of the most important observations, this is sort of the classic observation, that punctures this picture of a geocentric universe, is what's called retrograde motion. And so this is a series of images showing Mars's motion through the night sky over the course of many weeks. If the orbits of all the planets in our solar system are circular and around the Earth, then they should always go basically the planet should always go in the same direction at a steady rate. But instead, what happens occasionally for Mars and the other planets more distant from the sun than the Earth is that they will occasionally turn around and go back the other way. So here Mars is headed in one direction, and then at some point it'll stop in its orbit, go back the other way for a few weeks, then stop, and then continue on in its original direction. This is called retrograde motion, and it was very hard to reconcile with Ptolemy's picture of a geocentric universe. You can see that if all the planets are embedded in these circular orbits around the Earth, it's very difficult to explain how they would stop, turn, and go back the other way occasionally. And so observations like this, like the retrograde motion of Mars, prompted astronomers in the 15 and 1600s to begin questioning the geocentric universe that had been promulgated for hundreds of years at that point. And two particularly important astronomers in this story are Johannes Kepler and Tycho Brahe, pictured here. So here's Kepler and here's Tycho Brahe. I've put a link here to a really neat clip from the original Cosmos documentary with Carl Sagan that describes the relationship between Kepler and Brahe. Brahe was a very proud Danish royal astronomer. He was a genius at observational astronomy, especially in the 1500s. And this is before the advent of telescopes. So Brahe conducted decades of very, very precise naked eye astronomical observations, collected an enormous catalog of observations because he wanted to understand the structure of the universe. Brahe had a very particular model in mind for what the universe looked like. It wasn't quite exactly what Ptolemy had. It was geocentric, but geocentric in a little more complicated way than Ptolemy had in mind. And so to bolster that picture of the universe, he collected decades of observations without a telescope, all by hand. all with his naked eye. But he had trouble assembling those observations, the positions of this planet or that planet, this star or that star in the night sky, assembling all those observations into a coherent picture of the structure of the solar system. And so at one point he hired a Swabian, this is German, astronomer, Johannes Kepler, to come and work for him. Johannes Kepler was at that time a relatively well-known um, mathematician and astronomer himself. He was a genius at mathematics in a way that Brahe just really couldn't approach. And so Brahe hired Kepler to analyze his observations, to help him assemble this picture of the universe. But Brahe was a very jealous guy. He understood that Kepler, at some level, Brahe, I think, understood that Kepler was a better mathematician than him. And Brahe was famously jealous about his mathematical abilities. It's hard to see here in this picture, but Brahe actually wore a nose made out of gold. So it was like a mask, basically, that set on his face, and there were hooks that went behind his ears and held his nose on, made out of gold. And the reason he had a golden nose was because when he was a student, a mathematics student in his heyday, he'd actually gotten in a sword duel with another student over who was the best mathematician. So they both said, I'm the best mathematician, I'm the best. And the other guy chopped Brahe's nose off. So Brahe actually had to wear a golden nose in his later years because he was defending his mathematical abilities. So you can imagine he was a little worried about hiring Kepler, even though he knew he needed his help. Well, eventually, Brahe actually ended up dying, probably partly from his revelry. He was a partier. He liked to drink, and he probably suffered some kind of a bladder infection, it's thought, and ended up dying. And Kepler kind of made off with his catalog of observations. It's not entirely clear the legality of Kepler's acquisition, and Brahe's family was not too happy that Kepler ended up with this catalog of observations. But in any case, Kepler took the observations back to Germany from Denmark and spent the next almost decade analyzing Brahe's observations, and came to the conclusion that Ptolemy was wrong, that Brahe was wrong. The universe was not centered on the Earth. The universe, that is the solar system in this time, was centered on the sun. And the orbits of the planets were not circles, they were ellipses. And so Johannes Kepler published his so-called laws of planetary motion. The first two he published in 1609 in a document that was called Astronomia Nova, the New Astronomy, after analyzing Brahe's observations for about 10 years. So what Kepler realized was that the planets have these orbits that are like circles but kind of elongated in one direction, and that the planets don't orbit the Earth, they orbit the sun. And so his first law of planetary motion is that planets orbit in ellipses. Now, Kepler did not understand why the planets orbited in ellipses. He did not understand what gravity was. This is in the late 1500s. Sorry, this is in 1609. So this is the early 1600s. This is before Newton came along to explain gravitational attraction. So Kepler did not know what caused the planets to orbit the sun. But some forces were understood at the time. Magnetism, for example, was sort of known about, even though it wasn't very well understood. And so Kepler believed there was some form of magnetism that drew the planets toward the sun and kept them in this orbit. But he didn't understand why the planets kept moving around the sun. He understood that the planets would be drawn to the sun, but he didn't understand why they moved around and around the sun. And he actually believed that the sun's rotation, which had been observed by that time, that the sun's rotation somehow stirred the planets up in their orbits and kept them moving tangentially around, and then the sun's magnetism somehow kept the planets drawn toward the sun. And so this combination of stirring motion and attraction to the sun is what gave the planets their elliptical orbits. But he didn't know how to connect those two things up. An important thing that Kepler did not understand was that planets, as they orbit the sun, have an enormous amount of inertia. And so you probably know that once you start a heavy body moving, it likes to keep on moving in a straight line. Well, that's not something that Kepler really understood. And so he had to invoke this stirring motion of the sun's rotation to explain the tangential motion of the planets in their ellipses. One person who did understand inertia and was a contemporary of Kepler, in fact, was Galileo. So Galileo Galilei was an Italian astronomer and physicist who was a contemporary of Kepler. In fact, they actually traded letters. They sent letters back and forth. Galileo was a very accomplished astronomer, and in fact, you probably know, Galileo was the first to take a telescope and point it at the sky. Up until then, the early 1600s, telescopes had primarily been used as military weapons and used at sea for ships to sight land, or for someone on the land to sight a ship. No one had really, before Kepler, one other person, in fact, but Galileo was very famous for actually taking the telescope and pointing it at things in the sky. And one of the first things that he discovered by pointing a telescope at the sky were the large satellites of Jupiter. And so this is a page from the publication that Galileo wrote and got published in 1610 called Sidereus Nuncius, that describes his observations of the satellites of Jupiter, the major satellites of Jupiter. So you can see here's Jupiter, and then these little stars are the satellites of Jupiter. We now call these little stars the Galilean satellites. So these are, excuse me, Io, Europa, Ganymede, and Callisto. We now call them the Galilean satellites. But when he first discovered them, Galileo referred to these as the Medicean stars, because the Medici family was his like rich patron there in Italy, and so he was honoring them. So Galileo had discovered these objects through astronomical observations, and so these kinds of observations, bolstered by Kepler's analysis, helped to build this picture of a solar system that was centered on the sun and not the Earth, that had planets in elliptical orbits around the sun. But Galileo did not believe in Kepler's explanation of this mysterious pull of the sun on the planets. He didn't believe in what's now called action at a distance. He didn't believe that the sun could somehow transmit this mysterious force through empty space and pull the planets toward it, keeping them in orbit. So Galileo didn't believe in essentially what we would call gravity today, because he didn't understand that you could transmit a force at a distance like that. But unlike Kepler, Galileo understood inertia. And so Galileo had actually, in addition to his observations, astronomical observations, conducted a variety of experiments, both in his lab and in his mind, to try to understand how objects, once in motion, will continue to move. And so this is an illustration of a thought experiment that he did, and probably an actual experiment too. Galileo would roll balls down ramps to see how they moved and how they accelerated. And one thought experiment he had was, imagine rolling a ball down a ramp that then hits a flat region and then goes back up the other side. Galileo knew that the ball would descend and then reascend up the other side of the ramp to about the same height as it started. And he pictured the idea of flattening the second ramp out until you had a ball that essentially just rolled down a ramp, and then it would continue rolling on in a straight line forever unless something stopped it. This is what we refer to today as inertia. Once you get an object moving, it's going to keep moving in a straight line forever unless something else acts to stop it. And so there was this really interesting, in my mind at least, disconnect between the understanding that Kepler had of the influence of gravity at a distance propagating through empty space, but a misunderstanding of inertia. And then Galileo understanding this inertia, but not really buying this idea that you could influence things at a distance through empty space. There was this important disconnect between these two ideas. Unfortunately, Galileo and Kepler both died before these ideas could be reconciled. Kepler died in 1630, and then Galileo died in 1642, before there was a reconciliation of these ideas. It took until Newton to synthesize his ideas about gravitational attraction and inertia. Newton was born in January of 1643, almost to the day a year after Galileo died. So Galileo died in January 1642, and Newton was born almost to the day a year later that Galileo died. I won't go into Newton's life history. It's a fascinating story. He was born in a small farm just north of Cambridge. This is actually a picture of the farm, Woolsthorpe Manor. He led a pretty unhappy childhood. That probably was part of the reason he was such a deep thinker, is because he didn't have a lot of friends. And eventually he made his way to Cambridge, as many intelligent men at this day did, to study and establish himself as just a brilliant mathematician and physicist. During a Black Death plague, the Black Death visited the British Isles in the 1660s, Newton was actually sent home, socially distanced from Cambridge, and he sat at Woolsthorpe Manor for almost a year, for more than a year, waiting for the Black Death to subside, the waves of Black Death to wash away throughout the country. And while he was at his familial estate, he did some of his most important work on the influence of gravity and inertia, basically assembling together what is today classical mechanics, some of the basic important ideas behind classical mechanics. And what he realized was that if you connect together Kepler's ideas of gravity, or action at a distance, with Galileo's results having to do with inertia, you could explain the orbits of planets around the sun by only invoking those two ideas, gravitational pull and inertia. He was prompted to this realization famously by gazing out during this year in exile at the garden there at Woolsthorpe Manor. Now, there's a story that Newton was sitting out under an apple tree and an apple fell on his head, and that's what's prompted his thinking about gravity. It's probably apocryphal. Newton never actually mentioned an apple in any of his writings, but he did mention looking out at an apple tree and thinking about gravity, thinking about what would happen as the apple fell to the earth, and how that gravitational descent of an apple could be related to the gravitational pull of the Earth on the moon. So I just want to talk really briefly about this insight that Newton had, because I just think it's brilliant to be able to connect the motion of an apple falling to the ground with the orbital motion of the moon around the Earth. And so this is kind of a thumbnail sketch of how this worked. So Newton realized through experiment that an apple falls to the ground at the rate of about 10 meters a second in the first second. So as it just begins to fall, that first second, it falls to the ground with a velocity of 10 meters a second. Now, falling toward the surface of the Earth, for an apple, that's a pretty simple idea. That's something we experience on an everyday basis. But Newton extended the idea a little bit further. He realized that the moon in its orbit around the Earth was also, in a way, falling towards the Earth, except that the moon is 60 times further away from the center of the Earth than the apple is. And so because the moon is 60 times further away, any gravitational attraction that the Earth has on the moon will be reduced in proportion to that distance. This is the really important insight that Newton had. And in fact, Newton, when he sort of plugged numbers into this idea that he had, as the moon circles the Earth, it's almost as if the moon has fallen a certain distance over a time. And he could find that approximately the moon would fall about 3 millimeters in a second, as compared to the apples falling 10 meters in a second in that first second. And so by comparing these two things, he realized that you could explain this difference in the rate of falling by saying that the gravitational pull from the Earth declines with distance, declines actually with the square of the distance between the gravitating objects. And these two numbers work out to be exactly what you expect based on that. About a factor of 3,600 times smaller for the moon's velocity than the apple's velocity. And so it's important to realize that what's happening for the moon is not that it's simply falling straight down to the center of the Earth the way that the apple does. What's happening is that the moon has inertia. So if you were to launch an object from a high mountain outward tangentially away from the Earth, it would try to fall towards the Earth, but because it has this forward inertia, it doesn't fall immediately straight down from where you shoot it off. And if you can get an object moving fast enough around the Earth, then it will have a high enough inertia that gravity cannot just immediately pull it down to the surface of the Earth. Instead, that object will go into orbit around the Earth, like the moon does. And so this is the really deep insight that Newton had. This combination of gravitational pull will deflect the motion, causing it to go into a circle, but it's not strong enough to pull the thing straight down to the surface. So instead, an object like the moon stays in orbit because of its inertia. And so based on this important principle, Newton was able to explain Kepler's observations that the planets orbit in these ellipses. In fact, he showed that once the orbit of an object around the sun was established, the shape of that orbit, if it were just that object and the sun, the shape of that orbit would never change. In other words, if you just had a planet around the sun orbiting forever, the shape, orientation of that orbit would never change. And in astronomy, we would characterize the shape of a planet's orbit by referring to what are called the orbital elements. Now, I won't go too much into any detail about what the orbital elements are, but suffice it to say that describes the shape and orientation of the orbit. And if it were just a planet and a star by themselves together forever, the orbital elements would remain a constant for all time. Newton's discoveries, along with the telescopic discoveries of Galileo, prompted a golden age of telescopic observations and discovery. Now that basically anybody could take a telescope and point it at the sky, almost anybody could discover something important because nobody had done that before. And so, for example, one of Newton's contemporaries, Robert Hooke, pointed a telescope at Saturn and realized this strange oblong-shaped planet that Galileo had seen was in fact Saturn with rings. He realized there were rings suspended around Saturn. And so this is a sketch that Robert Hooke made in 1666, showing the rings of Saturn that he helped to discover. The mid 1600s, late 1600s, early 1700s became this time where basically anybody with a little bit of money and a little bit of time could build their own telescope and conduct revolutionary observations of astronomical objects. And so one such person was William Herschel. He was a German-born astronomer who actually moved to Britain at one point to pursue a career in music. William Herschel was actually originally a composer, and I've linked in the presentation here to a composition that he gave. I'll make sure this presentation is posted on my website so you can see it. But Herschel was actually a composer initially, and he moved to Great Britain at the age of 19 to pursue a music career along with his sister. But Herschel's real passion was not music. It was astronomy, and he became one of the world's foremost makers of telescopes. Actually, people paid him to make telescopes for him because he became so good at it. He was also a really big thinker. He had these really big ideas about the structure of the universe and how he could conduct astronomical observations to try to understand what the shape of the universe was, where there were lots of stars, where there weren't stars, these kinds of pictures. And so he conducted a variety of observations. He conducted some of the first astronomical catalog observations. So he basically did these enormous surveys to try to measure the positions of objects in the sky very carefully. And one night in 1781, he noticed an object, a curious object, in the constellation Gemini. I'm showing here what that looked like back in 1781 March. This is a strange object in the constellation Gemini, a star that he didn't expect to be there. So he pulled out an eyepiece to increase the power of his telescope and found that the object had a disk. Well, that was not what you would expect for a star. So it must be something else. And in fact, when Herschel first observed the planet Uranus, he thought it was a comet. So he noted in his manuscript that he had discovered a curious, either nebulous star or perhaps a comet. And he wrote some other astronomers, in particular the astronomer royal at the time, Neville Maskelyne, to ask him about this object. It's some strange object. Maybe it's a star. I don't know. It's probably a comet. Um, Maskelyne realized almost immediately that Herschel had not found a comet because there was no tail. They didn't see a tail. It wasn't a star because no one had ever observed a star that had a disk before. Maskelyne realized that Herschel in 1781 had found a new planet. Now, because Herschel was the one to discover the planet, he was initially given the honor of naming the planet. And he, like Galileo before him, wanted to name the planet after his patron, who was King George III. And so he originally named the planet Georgius Sidus, which is the Georgian star, to honor the British monarch. By the way, this King George, this is the same King George who, at this very time as Herschel discovered the planet, was at war with the American colonies. And in fact, March 1781, the American colonies had just passed the Articles of Confederation. So this is a pretty active time in history. Of course, the name Georgian star for a planet was not very popular with the rest of the astronomical crowd, particularly outside of Britain. And so there were several other alternative names suggested. In fact, one Swedish astronomer, Prof, suggested the name Neptune for this planet. But finally, the name was selected from this suggestion by the German astronomer Bode, who suggested Uranus for the name of this new planet, because Uranus is the father of Saturn, and Saturn is the father of Jupiter. This sort of made a very nice, coherent structure for the outer solar system there, Jupiter, Saturn, Uranus. And so eventually that name was adopted, but it was actually 60 years before Uranus was called Uranus. So many, many years you would see this planet referred to by multiple names in the astronomical catalogs. The first observations of Uranus's orbit were published in 1783. So keep in mind that the planet was only discovered in 1781. And so I'm showing you here, this is the observation, this is where Uranus was when William Herschel found it. And then this is where Uranus was in 1783 when the first orbital calculations were made, first calculations of its orbit. And so you can see it's only 2 years of observations. Uranus's orbital period is 84 years. And so if you want to get a really good fix on the orbit of this object, what you really need is more than 2 years of observations. And so they only had 2 years of active observations there in the 1780s, but the astronomer Bode, who had suggested the name Uranus, came back and he wondered whether Uranus had not been observed before by accident. Maybe previous astronomers had observed Uranus thinking it was a star and not realizing it was actually a planet. And so what Bode did was he took this initial orbit from this observational baseline between 1781 and 83 and combed earlier star catalogs to look for objects near what might have been the orbit of Uranus that were seen once and then not seen again. So he combed through these star catalogs to find things that were looked at once and then not actually observed again. And so he almost immediately found observations conducted by the German astronomer Tobias Mayer, who reported seeing a star in 1756 in the constellation Aquarius that was not seen later. So Mayer had actually observed Uranus in 1756, but had not made a careful enough study of that region to realize that he'd actually seen something that was moving. Bode's work uncovered observations of Uranus extending back to 1690. So Uranus had actually been observed like a half dozen times before it was actually discovered, but each of the astronomers who observed it had not gone back to carefully check that region of the sky and to see that this thing was in orbital motion. And so when these observations were collected all together, they had something like 100 years of observational baseline by combining the recent observations from the 1780s with these ancient observations going back to 1690. And so based on these observations, astronomers were able to begin to construct a much more accurate orbit for the planet Uranus. So scientists, astronomers throughout Europe were chugging away, doing really great work in addition to learning about Uranus. And then Napoleon came along and decided that the French should be in charge of all of Europe. And so as his 19th century came on, Europe descended into the chaos of the Napoleonic Wars, and this, as you might imagine, disrupted scientific progress. I've just got this beautiful painting here of the Battle of Waterloo. Scientific research during this time in all fields slowed, and rather than conducting expensive and in some cases dangerous astronomical observations, astronomers essentially retreated to their libraries. And in many cases, what they did was they collected additional archival observations of the planet Uranus, again, where it had been observed prior to its discovery, helping fill out the orbital constraints. And so I just want to show you here that I just discovered this afternoon I could do this. So here's a plot showing the sky and then showing these pre-discovery observations of Uranus over the ages, going back to 1690. And you can see there were quite a few. And so with the end of widespread hostilities throughout Europe in 1815, this is the second Peace of Paris when Napoleon was finally conquered, beaten, work and correspondence among European astronomers picked up again because now everyone was in at war with each other again. And something was wrong. The comparison of these growing collection of observations with the ancient ones of Uranus made it clear that something was wrong with Uranus's orbit. It was not orbiting the way that Kepler and Newton said it ought to. And just to give you a sense for that, I found a plot. Here's a plot of position of Uranus versus the year of an observation. And these observations that were made in this era, they could be matched up very accurately with some reasonable precision to the orbit that you would expect based on Newton's laws. But if you looked at these ancient observations going back to the 1690s, the orbit didn't match up at all. So something strange had happened. Uranus's orbit had changed dramatically from 100 years ago, and it wasn't clear what had happened. This discrepancy, the Uranus discrepancy, was noted by several prominent scientists, including Mary Somerville, who's a Scottish-born writer and polymath. She was one of a handful of women who was a member of the European Republic of Letters during this time. And she was actually called the first scientist. The word scientist was invented by William Whewell of Cambridge to describe her. Because she was a woman, she wasn't really allowed to be a professional natural philosopher at this time. So she spent a lot of time actually writing for the public about the progress that was being made in science. These books became very widely popular. Her most famous book, in fact, was called Connections in the Physical Sciences. And it just described kind of the variety of cutting-edge scientific research that was going on at the time, and made it accessible to the public. She remarked on this Uranus discrepancy in her 6th edition of the Connections in Physical Sciences, 1842. She said, if after the lapse of years, the tables, that's the tables describing Uranus's motion, formed from a combination of numerous observations, should still be inadequate to represent the motions of Uranus. The discrepancies may reveal the existence, nay, even the mass and orbit of a body placed forever beyond the sphere of vision. So here is Mary Somerville in 1842 speculating about the existence of another planet beyond the orbit of Uranus. She wasn't the only one to suspect this. There was maybe something else out there that we hadn't seen before. Well, one person who read Mary Somerville's book, Connection in the Physical Sciences, was John Couch Adams. So John Couch Adams was a British mathematician and astronomer who arose from very humble origins. He was born and grew up on a small farm in the west of England in Cornwall. Let's see. Here's a picture. In fact, here he grew up near the village of Lanneast on a tenant farm. He was the eldest of 7 children. There were a lot of kids in this family. And here's a picture actually of this just beautiful hilly country there in Cornwall. He showed an early aptitude for mathematics. It was very clear early on that he was a genius at math. For example, after witnessing one of his performances, a neighbor of his father declared that if John were my boy, I would sell my hat off my head rather than not send him to college. And so John Couch Adams's family was very keen to send John to college, college being essentially Cambridge or Oxford at the time. And so they worked very hard actually to gather the resources to send John to college, and he was able to enroll in Cambridge in 1839 at the age of 20. So he was a little older than most of the other college students, but he still managed to get there. And while in college at Cambridge, Adams encountered the Astronomer Royal George Bedell Airy. Airy was 20 years Adams's senior. Oh my goodness, I'm missing a. Oh, I'm sorry. Here we go. I had a few things that I had written down here. So yeah, John Couch Adams's family spent a lot of time and effort on the farm to raise additional funds to send Adams to college. In fact, they had basically passed a hat around the village to try to get the money to send him. And Adams enrolled at Cambridge on a scholarship at the age of 20. He excelled while he was at Cambridge, not surprisingly. For example, on the infamous Tripos mathematics examination. This is actually a famous exam that's given to Cambridge undergraduates. It's still given even today. It's supposed to be one of the hardest exams. I don't know much about it except that it's supposed to be very hard. Adams took this exam and basically aced it. He scored at the top of his class with twice as many points on his exam as the next examinee down. So he was far and away the most accomplished at this test. He earned the title Senior Wrangler. It turns out that in Cambridge, this Tripos sorts the students out in this ranking, and the top student every year gets Senior Wrangler. The student at the very bottom is called the Wooden Spoon and is paraded. I don't know if they still do this, but they did it at the time. Is paraded through Cambridge carrying an enormous wooden spoon for the honor of being last in the class. And so while at Cambridge, Adams encountered George Bedell Airy. He was the astronomer. Airy was the Astronomer Royal from 1835 to 1881. He was also the Senior Wrangler in his day as a Cambridge undergraduate. And Airy had published this very important report to the British Association for the Advancement of Science, which had just formed in the early 1830s. Airy was in a desperate state over the state of theoretical physics for Britain since Newton. So Britain had, of course, this amazing physicist, Newton, who came along and completely revolutionized science, created this very important framework for physical theory. And basically since then, since the 1660s, early 1700s, Airy was worried that Britain had not contributed any significant developments to science. He wrote in this report in 1832 to the British Association, "What has England contributed to the progress of astronomy? I fear that the answer will not be very satisfactory." This is sort of classic British understatement. Most of the important recent developments in science have been led by the French and German physicists and mathematicians, including Laplace and Lagrange, who were French astronomers, and they had developed a theory of orbital motion that complemented Newton's ideas. Essentially, if you have a planet in orbit around the sun, the orbital motion is very simple. It's just this ellipse forever. But if you have multiple planets in the system, now the planets will begin to interact with one another and can change their orbits mutually. This is called the theory of perturbations. And this was developed almost entirely in France, independent of any British input. It had been used very successfully prior to the 1830s to explain interactions between Jupiter and Saturn and very small changes in their orbits over time. It had even been used to explain some, but not all, of Uranus's discrepant orbital motion. And so the report that Airy published to the British Association also mentioned very briefly this Uranus discrepancy. Well, once Adams was an undergraduate at Cambridge, he happened upon Airy's 1831 report in a Cambridge bookshop, and it seems to have fired his imagination because he wrote in his diary in 1841, July, upon encountering this article, "Formed a design in the beginning of this week of investigating as soon as possible the irregularities in the motion of Uranus to find whether they may be attributed to the action of an undiscovered planet." And this is just a really neat, this is a scan of Adams' entry in his diary. After graduating from Cambridge in 4 years, Adams won a fellowship to stay on at Cambridge and support his continued studies, and also to begin this search for a planet exterior to Uranus. So how was he going to search for this planet exterior to Uranus? Well, he was going to use this perturbation theory. So this is a diagram kind of illustrating very simply how perturbation theory works. So here's this circle here, this portion of a circle represents the orbit of an interior planet. And then this portion of the circle here represents the orbit of an exterior planet. So as I showed you earlier, there's a gravitational pull between the sun and the planet, which causes the planet's orbit to be elliptical. But if there are additional gravitational pulls, shown here as these F arrows, that can perturb the orbit of the planet and change it very slightly over time. So what happens, the way we think about this in astronomy, is that the orbit of the planet is changing very slowly over time. Those orbital elements that I mentioned earlier don't remain constant. They very slowly change. They become what are called osculating elements. Osculating means, it comes from an Italian word, osculare, which means to kiss. So the orbital elements just sort of kiss one after the other, very slowly changing over time. We actually see this exact effect in the orbit of the moon around the Earth. This is a neat little video I found that shows that the change in the moon's orbital orbit as it circles the Earth. So here's the Earth, and there's the sun. Here's the moon's orbit. The orbital plane for the moon is tilted slightly relative to the orbit of the Earth. So that's going to be shown here. And because of the gravitational pull of the Earth and the sun together, the moon's orbit, which you can picture as being this flat plane, actually regresses around. So it revolves around the Earth. So the moon revolves around the Earth once a month, but the orbit of the moon sort of slowly changes itself over the course of about 18 years. And this is one of the effects that gives rise to the changing solar and lunar eclipses that we see throughout the course of the year. So this is that perturbation theory. And this is the technique that Adams used to predict where a planet would have to be exterior to Uranus to explain this discrepant motion. He used the theories of perturbations to calculate exactly where a planet would need to be, and he managed to complete his calculations by fall 1845. So keep in mind, he enrolled at Cambridge in 1839, he graduated in 1843, and then 2 years later, he had a complete theory of where an unseen planet would have to be in space in order to explain these discrepant motions for Uranus's orbit. Adams was a genius at mathematics, but he didn't have a sophisticated observing apparatus to go look for this object where he predicted it to be. And so he was eager to engage with an observational astronomer to follow up on his prediction. So he went to none other than Airy himself, approached George Bedell Airy, at least tried to convince him to look for this predicted planet. Adams attempted to approach Airy multiple times with his solution, and with no success initially. For example, in 1845, October, Adams tried to deliver the results of his investigation a month after he'd completed them in person to Airy at the Greenwich Observatory, which is pictured here. Adams, was this young student just out of college, approaches the door of this very eminent astronomer royal, boom, 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 knocks on the door. The butler answered the door and told him, I'm sure very curtly, the astronomer royal was at dinner and could not be disturbed. It turned out that Airy had a stomach ailment, and his doctor had recommended an early dinner undisturbed. And so Airy's butler sent Adams away with this prediction for a new planet that no one had seen before. Adams was forced to relay his results to Airy by mail, by the post. But Airy was not impressed with this 26-year-old astronomer he'd never heard of, and suggested that there might be some other consideration that Adams had not taken into account, which could explain Uranus's discrepant motion. Airy was not buying this explanation initially. And Airy didn't buy the explanation that Adams proposed until he heard someone else propose it. Airy didn't respond seriously to Adams' entreaties until he received an analysis of Uranus's discrepant motion in June of 1846. So more than 6 months after Adams completed his initial calculations. This time, the calculations came from Urbain Le Verrier, who was a French civil servant scientist, an astronomer himself. In a stunningly precise calculation, Le Verrier also analyzed the Uranus discrepancy and predicted the position of the unseen planet to within about 10 degrees in the sky. So 10 degrees, that's still a wide range. But the thing that really convinced Airy that he might have something here is that Leverrier's calculation predicted the exact same spot to within 1 degree of what Adams had said. There was a planet there, and now Airy believed it. This agreement finally prompted Airy to organize a search for the planet. But Airy was not the most passionate and he was not a rash man. He was the type of person to approach a problem very, very carefully and methodically. So instead of employing the Greenwich Observatory where he was stationed, he asked his colleague at the Cambridge Observatory to start a meticulous and methodical search of the region of the sky where Adams predicted this planet was, but not exactly where Adams said it would be. Airy mapped out this very meticulous and methodical survey for his colleague at the Cambridge Observatory to conduct, slowly sweeping the region near where Adams said the planet ought to be, and looking for objects in orbital motion. Airy believed that the best way to find the planet would be to watch for its motion relative to the background stars over the course of several weeks, instead of looking for a disk, which could be done basically instantaneously. And just to give you a sense for it, I found this diagram online. I actually don't know if this is accurate. I haven't checked it myself, but it looked pretty neat. So here's where Adams predicted the planet ought to be. Here's where Leverrier predicted the planet ought to be. So you can see they're very close to one another. Here's the orbit of Uranus, the sun, and all of that. Interestingly, Leverrier also had trouble convincing European astronomers to go looking for his predicted planet. When he published his calculation in 1846, French astronomers politely clapped, but none of them sprang to their telescopes to go find this planet. Leverrier, after sort of exhausting his options in his own country, finally contacted an astronomer, an astronomy student, Johann Galle, in Berlin, to ask for his help in finding the predicted planet. Galle, eager to make his mark on astronomy, implored his superior, Johann Encke, at the Berlin Observatory to let him search for the planet. Encke was also, a very preeminent astronomer like Airy, was not all that enthusiastic for the idea, but eventually, on a night when the telescope wasn't otherwise engaged, wasn't otherwise scheduled to be used, Encke deigned to let Galle conduct this search for the planet. And an astronomy intern, Heinrich d'Arrest, happened to be around when the search was proposed and begged Galle to let him participate. And so they turned the 9-inch scope to the spot, the very spot where Leverrier predicted it, and it was there with this high precision. The report of their discovery very quickly made its rounds through Europe, and Airy realized his grievous error in not springing to conduct a search. There was a variety of fallout. Unfortunately, we're running out of time here, so I don't want to keep it for too much longer. But Airy was castigated by the astronomical community, the scientific community in Britain. He tried to backpedal and tell a story where to give credit to Adams a bit for having made the discovery technically prior to Leverrier, even though it hadn't been published. But none other than Adam Sedgwick, who was one of the founders of modern geology, wrote to Airy to criticize his late action. In this letter after the discovery, I think this is 1846, Sedgwick says to Airy, "I am told that Adams's predictions came so near the mark that to a certainty the new planet would have been made out in a very few weeks. Is it true? If so, I must chime in with the pack of grumblers. To say the very least of it, a grand occasion has been thrown away." So Leverrier and Adams were actually given a lot of credit for the discovery of, although technically Leverrier had published first, there was enough records to show that Adams had also conducted an analysis. And so he's sort of given credit. It depends on who you ask, actually. Very shortly after the discovery, it was an enormous controversy. Now I think generally astronomers kind of give them credit as co-discoverers. In 1847, Queen Victoria actually offered John Couch Adams a knighthood, which he turned down. It's not entirely clear why. Adams was famously modest and was not all that wealthy, and so he probably worried about the cost of a knighthood. He went on to become a professor at Cambridge. Leverrier also received plaudits from throughout Europe for his brilliant analysis. And to their credit, Adams and Leverrier never were angry with one another. They met finally in June of 1847 at a meeting in the British Association for Advancement of Science. They never became embittered. They were friends to the end of their days. And now we have a planet at the edge of the solar system, Neptune. Maybe we'll talk about Pluto's discovery again at some point. So I'm happy to stop there and let's take any questions.
Hey, Brian, we didn't get any questions posted on YouTube just yet.
Yeah, great. Oh my gosh, I just realized how much I was talking. My throat is very sore. Yeah, this has been a passion for me, this story. And this is really just the tip of the iceberg. There's all these really fascinating stories underneath that you just can't tell in a I guess what has become a 40-minute lecture, a 45-minute lecture. I will be sure to post this talk on my website. So if you want to see any of these videos or any of these links, I'd be happy to make sure you could access to them. Please do join us in February on the first Friday then for Elisa Grossman's talk from Science News. I think it'll be really fascinating. And with that, I'm going to go ahead and end the stream. Thanks very much for attending.